Hello, this video is on atomic structure and electron configuration at A level. So in this video we're going to have a look at the atomic structure that you're used to seeing at Gcse, which is down here based on the Bohr model of the atom with the shells, and then we're going to make that quite a lot more complicated and look at how we arrange electrons at A level. So let's have a look at what we know so far at Gcse and move on from there. So here is your Gcse level model of the atom. If you want to, you could pause the video now, sketch this out and label where all the arrows are pointing to. Make sure that you know which bits are which. But I'm going to run through this now anyway so that we know what we're starting with. So, in the centre of the atom, this part here made up of, in this case, 9 particles. This is called the nucleus. So the nucleus is the very centre of the atom, and this really isn't to scale at all. The nucleus is really, really tiny compared to the size of the atom. So if an atom was this sort of size, you wouldn't even be able to see the nucleus. It's so small in comparison to the size of the atom as a whole. But the nucleus is in the centre. This is where all the mass of the atom is because it's made from the 2 heavy particles. So the nucleus is made of positive protons and neutral neutrons with no charge. So that's the nucleus, that's the dense, heavy centre of the atom. And then at quite a distance outside the nucleus, orbiting are the electrons, which are negatively charged. So here we've got the electrons. And at Gcse, you need to know the mass, relative mass, and the relative charges. And you still need to know this now, relative mass and relative charge of these particles. So as we've already said, electrons have a negative charge. Their relative charge is -1. Neutrons have no charge, and protons have a positive charge, which is +1. In terms of relative mass, protons, we can say that they weigh 1. Neutrons weigh the same, so they also weigh 1. And if protons weigh 1, neutrons weigh 1, comparatively, relative to that, electrons weigh very little. So we did say almost 0 or negligible. We can make that a little bit more detailed at A level, so we'll put 1/1840. So very, very light. So we still need to know those sort of details at A level. Now at A level, where the extra detail comes in is with the electron arrangement. So at the moment, we've got these electrons orbiting in discrete energy levels or shells. So you might call these energy levels, you might call them shells. So we'll label those as well. Okay, so these energy levels, we can number them. So the first energy level is the one that's closest to the nucleus. So this is energy level 1. And the next energy level out, or the next shell out, would be the second one. So this is shell 2 or energy level 2. And we could have more, so we could have a third energy level, a fourth energy level, and so on. But we start numbering closest to the nucleus. So this is the stuff that we already know, and a lot of it is still relevant. Even the idea of these shells being the first level and the second level, that's still relevant at A level. But what we do now is we kind of zoom in a little bit more and look in a little bit more detail at what's going on in each of these shells, and we break it down even further. So as you progress through your chemistry study, you start looking at different models of the atom, and it's a little bit like the timeline of the development of the atom. So we go from this idea that atoms in year 7 are solid spheres, a little bit like the Dalton model, where kind of like billiard balls or snooker balls, they're just a solid sphere with no real detail at all. As you start to progress to Gcse, and in some schools you do this a little bit earlier, you start to look at subatomic particles, and you start looking a little bit more at the model that Niels Bohr came up with, which is this planetary model of the atom with all of the dense, heavy stuff in the middle and these orbits of electrons going around the outside. Now we move even further on and we start looking at an atom that looks a little bit more like this, and this has orbitals. So I'm going to break that down a little bit. We're going to look at the shells to begin with. We're going to find out what orbitals are and how many electrons they can hold. But in this A-level model of the atom, we still have the nucleus at the centre of the atom, and we still have regions around the atom where electrons can be found, but these regions are a slightly different shape. They're not a straight flat circle anymore. They could be found in this sphere here. This is called the 1s orbital. They could be found in this sphere. They could be found in these lobes or this sphere. It's areas where electrons can be found, so it's a little bit more three-dimensional and a little bit more detailed than the Bohr model. So let's break that down. Let's find out how we can move from this model of the atom to this model of the atom. Okay, so let's go back to our Bohr model at Gcse and start to break this down a little bit more slowly. So here we've got the nucleus, which is fine. We're going to keep that the same. But around the outside, we have got energy levels or shells. So energy level 1 here, energy level 2 here, and you could have more. So we'll do, imagine we've got an energy level 3 here. It depends how big your atom is and how many subatomic particles it has. So you could have a third one as well. Now, each of those energy levels or shells is made up of subshells. So if we look at the energy levels as a whole, each of them is broken down into up to 4 different subshells, and we denote those, or we call them, the S subshell, the P subshell, the D subshell, and the F subshell. These are subshells or sublevels. So let's have a look at what each major energy level has in terms of subshells. So the first energy level, or the first shell, this red one here, it only has one sublevel, and that's S. So it's got an S sublevel. The second energy level has S and it has P. And the third sublevel has S and it has P and it has D. And we're not going to go much further than that at the moment because we don't need to worry about the F ones anyway, because they're a little bit too complicated at A level. Okay, so although we can't see it in this particular diagram, we know that in this shell here we've got one sublevel, and in this shell we have got 2 sublevels, and in this shell we have got 3 sublevels. But they're broken down even more into something called orbitals. So the S sublevel has orbitals that look like this. I'm going to show you the shapes of them because then it helps you to remember what you've got. So the S sublevel has one orbital that is spherical, it's round, okay? So this is a region of space where an electron can be found, and in each of these diagrams that I'm going to show you, the nucleus is still at the centre, okay? So we've got an S orbital within the S subshell. For P subshell, we actually have 3 orbitals, and they're a slightly different shape. Okay, so in the P sublevel or subshell, we have 3 orbitals, 3 regions of space where electrons can be found, and they've got this funny kind of shape here. So this is one P orbital, this is another P orbital, and this is another P orbital. These 3 different regions of space are all found in the P subshell. Okay. Now the D sublevel has 5 orbitals in there. So I'll try and show you the shape of them. They're a little bit more tricky to draw, and then we're not going to bother with F because it's too complicated for me. So the D sublevel or subshell has 5 orbitals, and this is the sort of shape that you've got. So they're kind of like doubled up P orbitals, all in different sort of arrangements. Okay, so if we go back to our energy levels, because we're not going to bother with F because it's too complicated. If we go back to our sublevels, energy level 1, we know that it's got an S orbital. Looks a little bit like this. So our S orbital in the first energy level is spherical, it's round, looks a bit like that. And that's all we've got, just that one energy level, one orbital within that energy level. Okay. On the second shell, we've also got an S orbital, which is still spherical, but it's a little bit bigger because further out from the nucleus. So we've got this region of space where electrons can be found. And it looks a little bit more sensible if I put an outline on it. But you've also got a P sublevel as well. And remember, the P sublevel is made out of 3 orbitals. So I've drawn them separately here, but you can imagine they all sit on top of each other with the nucleus at the centre. Okay, so we have got a P orbital that way. Let's draw around it so you can see where it is. We have got a P orbital that way. Looks like that. And we've got a P orbital kind of on the diagonal that looks a little bit like that. And they are all spaces in the second energy level or second shell where electrons can be found. So let's label those as well because they're also p orbitals. There we go. In the third energy level, we've got s orbitals and we've got p orbitals, but we've also got d orbitals as well. So it gets even more complicated. So in the third level, in our green level, we have got an s orbital, which we know is round. It's going to be bigger again. So we've got this space where electrons can be found in the third energy level. And sitting on top of that, we've got p orbitals. So again, we've got the up, down, left, right, and the diagonal one. So I'll put those in as well. And we've also got the d sublevel as well. So I'll draw those underneath so you can see what we've got in full. So these are all the spaces where electrons can be found within the d sublevel, and they're called d orbitals. So let's split those up so that you can see which shell or energy level is which. Okay, so that's how it's broken down. So we've got the energy levels which we met at Gcse, just 1, 2 and 3, nice and simple, moving out from the nucleus. Now we know that they're broken down into s, p, d and f subshells, and that within those subshells we have orbitals that are all different shapes. So in the s sublevel, the orbitals look like this. In the p sublevel, the orbitals look like this. And in the d sublevel, they look like that. And in the f sublevel, we're not going to go there. So these ones are orbitals, and an orbital is just a space where electrons can be found, and that's why we know the shape of them. Okay, now we're doing electron arrangement or electron configuration. We're trying to figure out where the electrons sit. So it's important to know what each of these orbitals can hold. Every orbital, no matter what type it is, can hold 2 electrons. So there's 2 electrons that fit in here, 2 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 in there, there, and there. So every orbital holds 2 electrons. That makes things a little bit easier because so far it's been really quite complicated. Now, electrons, we know, have a negative charge. So if you want to stick 2 electrons into this space, the problem is that they'll tend to repel each other because they both have the same charge. So the electrons sit in an orbital, but they sit with opposite spins to each other. So one spins clockwise while the other one spins anti-clockwise, and that prevents them from repelling each other so much that they can't sit in the same orbital. So in the 1s orbital, so this is a 1s orbital, this is a 2s, a 2p, 2p, 2p orbital, this is a 3s orbital, a 3p orbital. We just give them the energy level number first so that we know which particular orbital we're talking about, because if I just say s, you don't know if I mean this one, or this one. So in the 1s orbital, we can fit up to 2 electrons, and they've got to have opposite spin so that they don't repel each other too much. So to denote that, so that we don't have to write electron clockwise, electron anti-clockwise, we can represent electrons using arrows to help us to understand which way they're spinning. So here we've got 1 electron, and here we've got another electron. And by drawing the arrows in 2 different directions, we're showing that they've got opposite spin. Okay, so we can also fit 2 electrons, and I tend to draw them as half arrows like this, in here. We can fit 2 electrons in here, 2 in here, and 2 in here. Make sure that the arrows are pointing different directions so that they've got opposite spin. So now we know where the electrons can go. So at Gcse, we were bothered with knowing whether they go in the first shell and how many, the second shell, how many, the third shell. Now we need to know which orbital they're sitting in within a sublevel, within a shell. Okay, so 2 electrons in each orbital. Okay, so there's pretty much everything you need to know so far about where the electrons actually go. We just need to be able to write out some electron arrangements for different atoms and eventually for ions as well. What I should say before we move on is that these shapes are here for you to understand why we're moving to a new A-level model of the atom, something like this, and you don't have to be able to draw them, you just have to realise that that's where the electrons are found. And now hopefully you can see where we've got these shapes in here. So this is our model of the atom with all of these orbitals sitting on top of each other. So right in the centre, closest to the nucleus, we've got the 1s orbital, which we know is round. A little bit further out, we've got the 2s orbital, which is round, but it's a little bit bigger, so that's this orbital here. We've also got some p orbitals, so we've got this one, up and down, and we've got that one, side to side, we've got this one, on a bit of a diagonal going through the board. So they're your 2p orbitals. 2p because it's in level 2, but there are 3 of them. So there's that one, and that one. But they're called 2p orbitals because they're in level 2. And if we move further out again, we come to this orbital, so we've got a 3s orbital. And if we had more electrons, we might have some more p orbitals, something like this, but a little bit bigger. And we might even have some d orbitals as well. So it's this idea of sublevels, s, p, d, and f, and the orbitals within them that takes us from this Bohr model to this new A-level orbital model of the atom. So the next thing to know, we know that shell 1 fills first, and then shell 2, and then shell 3 from Gcse. That's what we've learnt so far. But in terms of orbitals, we need to know the order of filling, because if we know that sodium, for example, has got 11 electrons, we need to know where are they sitting in each of these orbitals. Okay, so I've written out the different orbitals that we've got so far for each energy level. So as you read across, that's a whole energy level. So that's the first shell from Gcse, and we know it's only got that one s orbital in it. This one, we've got a 2s orbital, and we've got a 2p sublevel, so we've got 3p orbitals in there. The up-down one, the left-right one, and the diagonal one in the 2p sublevel. We have got the 3s sublevel, the 3p sublevel, and the 3d sublevel, all in energy level 3. And we've got an S, a P, a D, and an F sublevel, all in the 4th energy level, all in the 4th shell. Now the way to figure out, because it's not straightforward, you would hope that you just go fill 1s, and then fill 2s, and then fill 2p. It doesn't quite work like that all the way down. It's a little bit more complicated than that, so this diagram is going to help you to remember how to fill the orbitals. And what we do is we take some arrows and we go down diagonally from top right to bottom left through each row. So the first energy level that we're going to fill, if we go diagonally, we come to 1s first. Okay, so we're going to fill 1s. Then diagonally we fill 2s next. Okay, then we fill 2p. So far so good. 1s, 2s, then 2p. Then we fill 3s. Okay. Then, if we go diagonally, we fill 3p. And then, so far it's gone 1s, 2s, 2p, 3s, 3p. You'd expect 3d is going to come next, but if we keep going diagonally, it doesn't. We actually fill the 4s next. After the 4s, let's carry on with our diagonal lines. We fill 3d, then we fill 4p, then we fill 4d, and then we fill 4f. Okay. Complicated, but there you go. That's the order of filling of electron shells. So I'll show you again. We go starting here, following each arrow from the top right to bottom left. We fill 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 4d, 4f, and we carry on. If we've got 5th energy level, we would have that written in here as well, and you'd see where they fill as well. Okay, so a little bit odd because they don't just go energy level 1, energy level 2, energy level 3. It gets a little bit complicated here where we go from 3p and we start filling 4s before we fill the 3d energy level. And that's because of the energy associated with each of these orbitals, which I'll show you on the next slide. Now, before I move on, if you struggle with this and you really can't remember which order to fill the electron orbitals or the electron subshells, then do what I've done here. So write the energy level 1 subshells, then write the energy level 2 subshells, 3 subshells, 4 subshells, and so on, and draw these diagonal arrows, okay, from top right to bottom left, and it will tell you in order which electrons go where. So I'm going to leave that. I know it's complicated, but if we start using it, generally the penny starts to drop even when people are completely baffled at this point. So we'll see how we get on. Okay. Before we start writing some electron arrangements, I need to come back to the periodic table because this is going to tell us how many electrons each atom has got, and then we can figure out where those electrons go. But something that's handy to know, and you may need to answer questions on this in your exam, is that the periodic table is absolutely filled with patterns and things it can tell us. It's absolutely incredible how many patterns are in there. But there's another pattern that you may not have come across yet, and that is that we've got different blocks of the periodic table. So if I just colour those in so that you can see, this is one block. Okay, we've got another block which is over here. Okay, so 4 blocks like that. And this is really useful, partly because some people can use the periodic table to very quickly write out an electron arrangement, but also because it gives us some really important information. So this is called the S block, this is the P block, this is the D block, and this is the F block. Again, not in the order that you'd expect, but there you go. S, P, D and F block. And what this tells us is that if an atom is found in the S block of the periodic table, then its highest energy electron, its furthest out electron, will be found in an S orbital, in an S sublevel. If an atom's found in the P block of the periodic table, then its highest energy electron will be found in a P orbital, or in a P sublevel. Same with D, same with F. So this is quite useful. The reason the atoms are found in each of these blocks of the periodic table is to do with where their highest energy electron is found. Now, if you have a copy of the periodic table on you that you're using for your studying, it would be a good idea to highlight the S block, the P block, the D block and the F block. And probably from this diagram you can see why we don't bother with F block elements, because they're down here in the lanthanides and actinides, and they're just far too complicated and far too heavy. So let's arrange some electrons into orbitals and see if all of this bizarre stuff starts to come together. Now, drawing out the shapes of the orbitals all the time is a bit of a pain, especially given that you don't need to be able to do it. So instead of drawing circles and those double blobs for the p orbitals, each orbital is drawn here as a box. So this is a space where the electrons can be found. In the first shell, we've got just the s orbital. In the p shell, we've got an s sublevel and a p sublevel. So we've got the s orbital and the 3 different p orbitals pointing in different directions. So hopefully this diagram makes sense. In the third level, we've got the 3, we've got the s, we've got the p's, we've got the 5d orbitals, and then in the fourth energy level, we've got the s, the p, the d, and the f orbitals that we can fill with electrons, I should say. Now, here's where it gets really confusing, because in general, we seem to be getting higher and higher energy. But the 3p orbital, you'd expect the next highest energy to be in the d orbital, but it's not. The 4s orbital comes next and then 3d. So if you remember that diagram from the other slide, this one here, this is why we have to fill 3p, then 4s, then 3d, because the 3p is lower in energy, the 4s is the next highest energy, and then the 3d is higher. So it's a little bit odd, but that's because of this. 3p, then 4s, then 3d. And there are a couple of rules to help us to arrange electrons properly. The first one you already know a little bit about. You might not know its name, it's called the Aufbau principle. But the Aufbau principle tells us that electrons are put into the lowest energy orbital first. So just like you know, you always fill the first shell before you move out, and then you fill the next shell before you move out. This is the same idea, but we're just breaking it down into orbitals now. So the Aufbau principle tells us lowest energy orbitals have to be filled first. Okay, so let's choose an element and start arranging some electrons, and then we'll come across the other rule that you need to know as well. Right, so let's go for beryllium. Beryllium has 4 electrons, and we need to know where they go. If we were doing Gcse level, there'd be 2 in the first shell, 2 in the second shell. So Aufbau principle tells us electrons fill the lowest energy levels first. So the lowest energy level we have got, down in the bottom left corner of this diagram, is the 1s orbital. Remember, it's that round orbital. So we can put, remember, 2 electrons in any orbital as long as they are spinning in opposite directions. So here's 1 electron. So we're down to 3. And we can put another one in there as well, as long as it's pointing the opposite way. There's 2 electrons. So we've got 2 more to place. So the Aufbau principle tells us fill the lowest energy levels first and then you can move up. So let's move up to the next lowest energy level, which is the 2s. And remember, this can hold 2 electrons as well. So one has to be drawn pointing up and one drawn pointing down so that they've got opposite spin, and we've used both of those electrons. So that's where the electrons are arranged for beryllium. So if you're asked to give the electron arrangement of beryllium, then you just list where the electrons are and how many there are. So watch this convention. The lowest energy level is the 1s orbital. So we've got 1s, and in there are 2 electrons. So we put it up at the top. The next orbital is the 2s, and in there we've also got 2 electrons. So that is your final electron arrangement for beryllium. So instead of 2, 2, as it would be at Gcse, we now have this extra detail that tells us beryllium is 1s2, 2s2. And if you count up the little numbers at the top, the superscript numbers, that should give you your total number of electrons, because that's what you've placed. 2 of them in there, and 2 of them in there. And that's your final answer. Let's do another example. Okay, so let's have a look at nitrogen this time instead. Nitrogen has 7 electrons, so we need to place those into these orbitals. Remember that 2 electrons can fit in each orbital. So according to the Aufbau principle, we're going to fill the lowest energy levels first. So we can put 2 electrons into the 1s orbital. So we're now down to 5. 2 electrons can fit into the 2s orbital. So we're now down to 3, because we've placed 4 of the electrons. The next highest sublevel is the 2p sublevel. But the 2p sublevel consists of 3 orbitals all at the same energy level, because this is our energy axis here. They all have exactly the same energy. So we've got 3 electrons to fill, and there's different ways we could do it. So we could fill that orbital, and then fill that orbital. So that puts 2 electrons in there, 1 in there, and leaves the other p orbital empty. Alternatively, we could, because we can't get all 3 into the one box, so we have to split them up somehow, but the other thing we could do is we could put 1 electron in there, and put 1 electron in there, and put 1 electron in there, so that now we've got 1 in each orbital. So which one do you do? Well, Hund's rule tells us the answer to that question. Hund's rule says that electrons enter separate orbitals first, and they only pair up when there are no empty orbitals of the same energy. That means that the electrons would prefer to go 1 in here, 1 in here, and 1 in here, and don't pair up if they don't have to. So some people call Hund's rule the sitting on a bus rule. So if you think about sitting on a bus, if you get onto a bus, would you rather sit in a seat that's already got someone next to you, or would you take a seat all of your own? People don't tend to sit next to people on buses if there's a completely vacant seat available. So that's how some people remember Hund's rule, the sitting on a bus rule. But these are your 2 principles that help you to understand how to fill these electron shells. So we could have got confused here, but Hund's rule tells us 1 in each orbital is best. And that's because if you put 2 electrons into the one orbital, there's extra repulsion there, and you can avoid that by putting them into separate orbitals. So the electron arrangement for nitrogen is, remember, you list the orbitals. So we've got the 1s orbital first. In there, we've got 2 electrons. Then we've got the 2s orbital, and in there, we've got 2 electrons. Then we've got the 2p, just keep that as a whole sublevel, so 2p, and in there we've got 3 electrons. So if asked in an exam, what is the electron arrangement of nitrogen? It's 1s2, 2s2, 2p3. And again, let's check that 3 plus 2 plus 2 gives us 7, which is the number of electrons in a nitrogen atom, and that is how they are arranged. Now, if you've got the activity sheet in front of you, you've got 2 examples to do yourself on a diagram like this, one for silicon and one for calcium. So I'm going to ask you to try and understand what we've done so far, see if you can complete the electron arrangement diagrams for silicon and for calcium, and also, once you've drawn in the diagram, can you write it out as an electron arrangement in that sort of format? and then I will show you how to do them as well, just to check if you're getting it right. So have a go at the silicon one, and then pause the video, and I will show you how to do it. So here I've found silicon on the periodic table, and I know that silicon has 14 electrons. So let's see where we're going to place them. Well, we'll start with the lowest sublevel, just as the Aufbau principle tells us. So in the 1s orbital, we can fit 2 of those electrons in there. So we've used 2 of them, so now we're down to 12. We can fit 2 into the 2s orbital. Now we're down to 10. In the 2p, we're going to fill them according to Hund's rule, 1 in each orbital before we start pairing them up. So 1 in there, 1 in there, 1 in there. That takes us down to 7. We've still got some to fill, so we can put 1 in there, 1 in there, and 1 in there. We've now paired them up. That takes us down to 4 electrons left to place, so we can put 2 electrons in the next available energy sublevel, which is the 3s. So we've got 2 in there, we've got 2 left to place, and remember, Hund's rule tells us that the final 2, rather than pair them up and allow that repulsion to take place, put them in separate orbitals, just like you would sit on a bus in separate seats. So that is how the electrons are arranged in silicon. So we can write that out if you're asked for the electron arrangement of silicon. List the orbitals and tell us how many electrons are in them by putting the number of electrons superscript. So we've got 1s with 2 electrons in it, 2s with 2 electrons in it, 2p with 6 electrons in it, 3s with 2 electrons in it, and 3p with 2 electrons in it. And that is the electron arrangement for silicon. So hopefully that one made sense. Hopefully you were able to do it before watching this bit of the video. But now that we know this and we understand how to do it, you can move on and have a go at the calcium one as well. So have a go by yourself, and then I will work through it with you. Here we've got calcium taken from the periodic table, and calcium has 20 electrons. So the Aufbau principle tells us start with the lowest available orbital and fill that first. So 2 electrons can fit into there, takes us down to 18. Next one up, 2 electrons can fit into the 2s orbital. So we've got 16 left to place. 1 in there, 1 in there, and 1 in there. And then pair them up. That gives us 6 electrons in the p orbitals, so that takes us down to 10. The next available energy level is 3s, so we'll put a pair of electrons in there. We've now got 8 left to place. Then the 3p, according to Hund's rule, place them separately first. So we've put 3 in there, we've still got 5 left, so we can still pair them up. Pair them up, and we're down to 2. Now the next electrons, people who aren't familiar with the order of filling orbitals might go straight for 3d, because you would think 3s, then 3p, then 3d. But remember that the 4s is lower in energy than the 3d, so you have to fill that first. The Aufbau principle tells us fill the lowest energy orbital first. So 4s can take 2 electrons, so we will put 2 electrons into the 4s, and we've done them. We've used them all up. And if you have a look at the periodic table, as I mentioned before, the block of the periodic table that each element is found in will tell you where the highest energy electron is found, what type of orbital it's in. So I'll just show you the blocks again. So there's your blocks, and we're looking at calcium. Calcium is here, it's in the s block. That tells us its highest energy electron is in an s orbital, which it is. It's in the 4s orbital, that's where the highest energy electrons are. Okay, so this isn't helpful really to write out an electron arrangement, so let's write it out in that normal format with all of the different orbitals listed. So calcium, its electron arrangement is 1s with 2 electrons, 2s, 2, 2p, 6, 3s, 2, 3p, 6, 4s, 2. So that's the answer for the electron arrangement of calcium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And that's that one done. So I hope you were able to figure that one out as well. Now there are a couple of exceptions, because there always are, because nothing's ever straightforward, that I would like to show you before you go and practice some electron arrangements by yourself. So there are 2 elements that you need to be aware of where the electron arrangement is slightly different to what you'd expect. Okay, your first exception is copper. Now I will show you how you would expect copper to be arranged, the electrons in copper, and then I'll show you how it's slightly different and explain why. So copper has 29 electrons to place, and we'll just fill those really quickly, so I'll talk you through it, but nice and quick. Starting with the lowest, we put 2 electrons in the 1s orbital, 2 in there, we can fill that, 2 in there, and we can fill that. And then I'm going to check how many electrons I've used so that I make sure I don't use too many. So we've got 6, 8, 10, 12, 14, 16, 18 electrons used. So we've now got 11 electrons left to place. So the next available sublevel is our 4s. We know that that's lower than the 3d, so we'd usually start there. So let's fill that. We'll put 2 electrons in there. That takes us down to 9 electrons left. And remember, Hund's rule says fill them separately first. So put 1 electron in each of these. That takes us down to 4, and then we can pair them up 4 times. So we end up with that. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. So that's what we would expect the electron arrangement for copper to be. However, there is one additional rule that only really applies to copper and to chromium, and that is that full sublevels or half-filled sublevels are more stable than just partially filled sublevels. So an atom would aim to have either a fully filled sublevel, so something like here where there's no space left in this sublevel, or a half-filled one. Now what can happen here with copper, so we've got 9 electrons in here and we've got a pair in there. 1 electron can be promoted from the 4s into the 3d, and that would fill this whole sublevel. That one would be full, and this one would be half full, which is still reasonably stable compared to something that's only got 9 out of 10. So that's exactly what happens. One of these electrons that should go in 4s actually fills the 3d orbital instead, because it just gives that extra stability of having a full sublevel. It's just, honestly, it's just one of those things that's there to make things a little bit more complicated, but it's true and it does happen. So let's move that electron and change our electron configuration. So we take an electron out of 4s and we pop it into 3d. And that means that our electron arrangement is still 1s2, 2s2, 2p6, 3s2, 3p6, and then it's not 4s2 anymore, it's now 4s1. 4s1. And instead of 3d9, it's now 3d10, because that whole sublevel is now full. So this is the correct electron arrangement for copper, and it doesn't work quite the way I told you it would in the previous slides, and that's because of this idea that half-full sublevels and fully complete sublevels are a little bit more stable. So that's what happens with copper. And chromium does a slightly similar thing, so I'll show you chromium as well. Just keep these in mind, these are just the 2 exceptions, and everything else works the way that I've told you it will work. Okay, so your other exception is chromium. Chromium has 24 electrons, and let's place them as we normally would. So, lowest energy level first, fill that. We've used 2. Fill that. We've used another 2. Let's fill this, 1 in each. Then we can pair them up. We can fill this one. We can fill this one, 1 in each, and then pair them up according to Hund's rule. And then 4s is next, so we put a pair in there, and 1 in each so that they are separate. Okay, so that's what you'd expect chromium electron configuration to look like. It would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay. Now, remember what I said before, that half-filled sublevels or fully complete sublevels are slightly more stable, and here we've got 4 out of 5 if we wanted to half-fill the 3D sublevel. So the same thing happens again as happened with copper. One of the electrons that would be in 4s moves into the 3D sublevel so that we can half-fill the 4s and the 3D, rather than completely fill 4s and leave 3D with a random number of electrons in it. It's much better to have both of them half-filled. So exactly the same idea as with copper, except this time we're going for a half-full 3D sublevel rather than a complete 3D sublevel. Okay, so we'll take that and we'll move it over. So the 4s only has 1 electron in it now, and its other electron moves up into the 3D sublevel. So to change our electron arrangement, we've still got 1s2, 2s2, 2p6, 3s2, 3p6, but we've now got 4s1. And instead of 3d4, we've now got a half-filled 3D sublevel, so we've got 3d5. So that is the electron configuration of a chromium atom. Again, it's just another one that you need to remember. Keep those 2 elements in your mind when you're doing electron arrangements, copper and chromium. And that is how to do electron arrangements at A level. So absolutely tons of information thrown at you there, really, because you've now got sublevels and orbitals. I've shown you the shapes of them. We've got the Aufbau principle, we've got Hund's rule, and we've got this really annoying idea that the 4s energy level is lower than the 3D, and we have to fill it before we fill the 3D. It just all gets a little bit complicated. But what you really need to do now is just practice. So remember that each electron is represented by an arrow. If you're going to put 2 electrons into the one orbital, the arrows should be pointing in different directions to show that the electrons have opposite spin to prevent them from repelling too much. And you're filling in that sort of direction, increasing in energy all of the time. Now you just need to practice. So if you go to your activity sheets and have a go at drawing some of the electron arrangements, for now, just do the electron arrangements for atoms, neutral, uncharged atoms. Don't bother with ions yet, because ions are going to get a little bit more complicated, and you'll need a separate tutorial for ions. But apart from that, I mean, you can have a go at some of the ions. They get a little bit complicated when you get into the transition metals. You can try them if you want, but just be aware that there are other things that you need to learn first. But I hope that helped you more than it confused you. Have a go, try and practice, and make sure that you get loads of feedback to make sure that you're doing it right. And that's all for this tutorial.